So I picked some questions from the toolbox chapter of the ACS study guide. We'll switch to answering your questions in a sec if people have questions. But we will go through, I think, all three of these questions. So what needs to be added to balance the chemical equation for our very first question? First thing that I would point out, how many times have we actually balanced any chemical equation in OChem? We have not. And in fact, I would argue we have aggressively ignored balancing chemical equations. That doesn't mean it's not useful, and we'll get to the why it's useful in a second, which is why I think they're actually asking this question. So if we were to try and balance this, what do we need? What's missing? Okay. We're missing that SCH3. Okay. So we could go through and just say, well, that's what we're missing. We know more than that. Okay? Sulfur, being underneath oxygen, should have 2 bonds and 2 lone pairs. The lone pairs we can largely ignore, but we would expect 2 bonds in its neutral state. Right now, we're only showing it with 1 bond. Okay, so there's a couple approaches to how we could fix this. One option, actually I'll color those in black, okay, would be to acknowledge that we could have an extra lone pair and that this would then be negatively charged. That species belongs on the reactant side. Okay? What information does that give us? Okay? Did it give us that we did a substitution reaction, or did we already know that? We already knew that based off of the context of the information above. That Cl was replaced by something else. We didn't know what that something else was necessarily, okay? But we know it was a substitution. If we can recognize that that was the case, we can now start to put in not only what was missing, but this can now start to address the reagents necessary to complete the reaction. Sometimes those reagents are just what's missing. Put the piece in and you're done. Other times you have to have a little bit more precision behind it. Okay, so for instance, for this particular reaction, would that be equally valid? Okay, why not? Okay. Would that be equally valid? Okay. And now we've got a tough question. We're like, well, if we balance it, isn't it balanced? Yes, it's balanced. Does that mean it's equally valid? Okay. So some people are saying no. Why are you saying no? Or is it just gut? I mean, gut is fine. Okay. I got a gut from you. Her eyes are down. I saw your head no. Why do you think it's not equally valid?
You don't want to do hydrochloric acid on the product side?
We aren't technically forming hydrochloric acid at this point because we're showing that H plus flooding off on its own. That H plus could associate with anything else. So unfortunately, that's not a horrible answer, but it's really a non-answer. Isn't it still a substitution? You are also losing the H plus in the course of the reaction. What is the overall reaction? It's still substitution. It just requires an extra acid-base step. And if you look at the SN1 mechanism, very commonly it's accompanied with an acid-base step. Okay? So just because there's an acid-base step doesn't change the overall reaction. Isabel, you said no, and then you've been avoiding my eye contact since then. Gut feeling? Okay. How would we know? What should we be looking for?
Excess electrons.
Why does that matter?
Because you have to see what kind of mechanistic steps it takes to get there.
What kind of mechanistic steps it takes? I like that. Okay, we're talking about a substitution. Which are our mechanistic steps for substitution? Or mechanism, let's go with classes instead of steps. SN1 and SN2. Okay? Here we're being shown the overall reaction, so we don't know how many steps are happening along the way, so that's invisible to us. How do we differentiate SN1 and SN2 if we can't see the individual mechanistic steps? The stereochemistry. Solvent is a possibility. There's no solvent specified, so that leaves us kind of in a hole. Okay, what do you mean the stereochemistry? Yes, wedges and dashes are associated with stereochemistry. Why is that relevant to differentiating SN1 versus SN2?
So it can't put electrons in the same place as other.
SN2 is backside attack. SN1 is carbocation, and we know the carbocation is a p orbital above and below the plane, which would mean I'd get two products. In this case, how many products do I see? That one gets a bit of an interesting question, depending on how you wanted to phrase it. Okay, for those people saying 1, I agree with you, I would say 1. For those people saying 2, I get it. For those of you saying 3, I get it, but I don't care. Okay? The focus is on the organic molecule. Okay? So I'm really only getting one product. So just by showing a single product, they're starting to suggest it's SN2. They could be tricky in saying, well, maybe there's other products and we don't going to tell you that information. What other information could help you say this is SN2? And you did say it, Charlotte.
The SCH has. Oh, you want me to just keep going? Oh. Came in from the back
How do you know it came in from the backside?
because it's wedged.
We started wedge and we switched to dashed. We have a clear backside attack. All of that would suggest SN2. And if we're suggesting SN2, what kind of nucleophile do we want? Strong. Which of our two answers is a strong nucleophile? The top one. Okay? So when we're looking at balancing the equation, it's not really balancing. It's trying to get you to recognize what are the pieces that are missing so that we can now ask a more advanced question. That's why this question is sitting in the toolbox chapter. Do you recognize these patterns and how you can then manipulate those later on? Make sense? Okay. 7 and 8, I would argue, are sort of out of order. I would do 8 before 7, so let's take a look at 8. Okay, strong dipole-dipole. How do you have a dipole-dipole force? Difference in electronegativity. NaCl, is that going to be dipole-dipole?
No.
Okay, so difference in electronegativity is true, but it's also false, which means that was a bad thing to memorize. You need specificity behind your answer. What's the specificity you should be adding? Define a covalent bond. Non-metal to non-metal, that's true. Are there other types of covalent bonds? We have polar and non-polar. And in both of those scenarios, it's non-metal to non-metal. So is the non-metal definition useful? No. Okay. All it does is allow me to remove ionic, which I had already removed, and I theoretically should have already removed because what do I see in an ionic compound? Charges or metals. All right. So again, how do I have a dipole-dipole? We've suggested difference in electronegativity. Too vague. We suggested covalent. Also too vague.
Polar covalent.
A polar covalent bond. How do you know you have a polar covalent bond?
Difference in electronegativity and they're both nonmetals.
Both nonmetals and a difference in electronegativity. What's the electronegativity of carbon? So cool, we've got this definition of I want a difference in electronegativity, but you don't know any of the electronegativities. Again, what did we just discover? A bad thing to memorize. How do you know you have polar covalent?
Periodic trends usually.
What periodic trend?
Electronegativity increasing from left to right.
Okay, so hydrogen and carbon are nowhere near each other on the periodic table, right? we seeing the issue with the logical flow of the definitions you've been memorizing. How do we know we have a polar covalent bond? I wish someone had told me how to identify a polar covalent bond. So let's put it on its head. Are there other types of bonds? Or are all bonds polar covalent? Okay, what are the other types of bonds?
Ionic and non-polar covalent.
How do you know you have an ionic bond?
Is a metal.
Cool, we've identified that one pretty fast. I did throw in, we do have a caveat there. You got to watch out for charges. Typically, you're looking at metals, but they can throw an odd curveball in there and remove the metal and make sure that they're charged species instead. Okay? So you know ionic, great. How do you differentiate non-polar covalent from polar covalent?
No difference in electronegativity or little difference?
Okay, what's the electronegativity of carbon? Okay, I can't use that rule again. Referencing the raw electronegativity values isn't helpful if you haven't memorized the values.
I mean, it's carbon dioxide.
Carbon to hydrogen is defined as a non-polar covalent bond. Is that it?
Or like
And not just carbon-carbon, but also
substances.
oxygen-oxygen, fluorine-fluorine, chlorine-chlorine, okay, nitrogen-nitrogen, same to same. Okay? So what is polar covalent?
Anything else?
Okay? So if you've memorized 2 out of the 3, you know the third one is what's left. That's exactly what I told you to do from day 1. Okay? And from day 1 pointed out the flaws in electronegativity memorization. Okay? So we're looking for something that has polar covalent bonds, which are not ionic and not nonpolar covalent. So we can now go through and look at our answers. Do we see ionic in any of our answer choices? No? Well, that kind of sucked. We memorized something that didn't get an elimination of an it. Do we have anything that's nonpolar covalent? Okay. We actually have a lot of nonpolar covalent within it, okay? But you'll note that A is exclusively nonpolar covalent. So what we can kind of effectively do is go through and just erase the parts of the molecule that are nonpolar covalent, because those aren't relevant to me. Okay? So all 3 of those answer choices now have polar covalent. Those are all going to generate dipole-dipole interactions. Well, how do I know the answer then?
It says strong dipole-dipole interactions and not stronger. So maybe differentiate based on that.
And not stronger intermolecular forces. I mean, we have to read the rest of the question. Yes, okay. What are the other intermolecular forces?
Hydrogen bonding.
Hydrogen bonding. What's stronger than hydrogen bonding? Ionic, but we don't have to worry about ionic because there's no metals. Cool. So the only thing we have to look for is hydrogen bonding. Okay? Do any of those show hydrogen bonding? How do I know I have hydrogen bonding? I find a hydrogen that's chemically bonded to an oxygen, nitrogen, and fluorine. Do I have that? Yeah. Okay. Now what do I do? I would argue I'm a little nervous about this. I don't know if you all are, but I'm nervous about the phrasing of this question that they may or may not have done intentionally.
Well, the only other thing,
Go ahead.
well, it says specifically strong dipole-dipole interactions, so what would be a particularly strong one?
Okay. So what's going to generate a stronger dipole-dipole interaction?
Higher electronegativity.
Okay? A larger difference in electronegativity. We don't have those memorized, but we can take advantage of the trends because we've removed some of those non-existents or those counter trends like carbon and hydrogen. We've removed that with our nonpolar covalent. We spent the time to memorize something that didn't fit the trend pattern. Okay? So we could now compare carbon to bromine versus carbon to oxygen. Okay? It says strong dipole-dipole interaction. Which one's going to generate a stronger dipole-dipole interaction? What dictates it?
Difference in electronegativity.
Difference in electronegativity. So here's where something else could come into play. Memorizing the trend, but also memorizing another piece of information. But the trend would get us far enough. Okay? The trend is what? What's the trend for electronegativity?
Left to right.
So helium's the most electronegative.
Fluorine.
No, okay, so fluorine's the most electronegative. Okay? Then oxygen. Why would you say oxygen next? Instead of carbon. That the trend says the closer we are to oxygen, the more electronegative, right? Okay? So if we're now comparing here, the carbon isn't changing electronegativities, but bromine versus oxygen is. Okay, so what do I need to compare? Oxygen to bromine. Which one's closer to fluorine? Oxygen, which means which one has the larger electronegativity? Oxygen, which one's going to generate the larger dipole force? There it is. Okay, hold that thought for a second. Okay, what else could you have memorized? What are the three most electronegative elements?
Nitrogen, oxygen, fluorine.
Nitrogen, oxygen, and fluorine. Okay, fluorine being the most, oxygen next, nitrogen. If you had that memorized, which one's more electronegative, oxygen or bromine? Oxygen is the second most. You've got it memorized. There it is. You have your strong dipole. Okay? So far, okay? Okay, we're going to add a wrinkle to this in a second, but first Peyton's question, unless he's going to throw the wrinkle in.
I was just gonna say, couldn't D engage in hydrogen bonding? So
You're throwing in the wrinkle into this. So I would argue this question is not particularly clear within its statement here. Are we talking about the structure engaging in strong dipole-dipole interactions and not stronger intermolecular forces within a pure substance? Because within a pure substance, D's our answer. Okay? The strongest force that comes out is a dipole-dipole. It's a really strong dipole-dipole because we have a large difference in electronegativity. Okay? It's not going to get hydrogen bonding because there's no hydrogen bond donor in the pure substance. Okay? I would bet that's what they were asking, and they screwed up the clarity of the question. Okay? Because as Peyton brings up, what if it wasn't a pure substance? What if I mixed these substances with water? What interaction is going to be formed between the oxygen of our carbonyl and the hydrogen? That's now hydrogen bonding. That's a stronger intermolecular force. How do you answer that then if you're left in that gray area?
You'd answer with
I would assume purity within it. Okay? The other part that I would hope for is hope that somebody else is also looking at the exam from these hierarchical standards and being able to say, the phrasing of that's not so great. That could lead to confusion. Students might get that wrong. And be like, hey, let me clarify. Or you as a student that recognize that, is this pure or not? Be like, dude, Mike, I don't like this question. Oh, why do you like this question? Is this pure substance or not? Oh, you're right. That wasn't very clear. I didn't see that as pure. Quick shift. You now have the answer and you move on. Make sense? What were they fishing for? Well, easiest way to find out. See what they picked. For their answer, they picked D, the pure substance. Okay? Which does bring up another potential point. Tests aren't perfect. Okay? Particularly practice tests become even more imperfect because those questions aren't being tested out in a broader sense. Those are, throw some questions out here that touch on the subject we want without looking too deeply at it, because it takes a lot of time and effort to build those questions. Kind of, sort of? Hi. Question 7. Which solvent is least likely to dissolve the compound? Okay. This is going to bring in a whole layer of extra kind of pieces. If we're talking about dissolve, what are we referencing? Solubility. And what's our rule for solubility?
Like forces?
Thank you so much for the way you said that. Like forces, which means I need to look at the compound given to me, okay, because that's my known, and say, what are the forces? Okay, how do I identify forces? By identifying the bond types within it. So that ability to real quickly assess what bonds are present allows me to jump to the forces quicker. If I haven't built up that skill, I can't jump to that answer as quickly, and I now have to stepwise through each and every single one of those stages. This is why you're supposed to be doing practice along the way to improve that. So when we look at those, what kind of bonds do we see within that structure? Non-polar covalent, they're all carbon to carbon or carbon to hydrogen. Non-polar covalent bonds lead to what intermolecular force? London dispersion. So if I want this compound to dissolve, I want like forces. What would be the best force? London dispersion forces. So I would now go through my answers and look for the compound that had non-polar covalent bonds. This is great. I'm on a roll. I'm walking all the way through this, except what did I miss? It says least likely. So when I'm talking about like forces to dissolve, okay, I want the least similar force to LDF. What's the least similar force? Ionic. Okay. So now that we know that, what can we do? Now we can look at all our answers and look for ionic. Okay. What do we encounter as a potential issue? They're all written out as names. Are you responsible for those names? It's a shitty gray area, unfortunately. Okay? As far as I'm concerned, no, you're not. So what I will do is scan through, and when I see names like this, okay, these are all what technically you should be able to get hexanes, okay, but ethyl acetate, and you should be able to get water too, and acetone, okay, those two compounds, their naming, acetone number 1 is a common name, not IUPAC. You're not responsible for common names, period. Okay? So I should give you that structure. And then ethyl acetate as a name, actually it's still a common name because it's using we're just going to say I'll say, change the pronunciation, the ace prefix, okay, within it. Okay? That prefix is the same thing that's being used in acetone. Okay, and it does have a common name meaning. You're just not responsible for it. Okay, so those should be properly drawn out either as structures, or you should have proper names. That's not a proper name either, so we would fix that. Okay, so how do we fix? If I drew it for the other answers, I'm going to draw it for water. There's the ace part of acetate and acetone. There's the ethyl of the ethyl acetate. Okay? So there we go. We now have those structures. Now that we have those structures, do we see any ionic forces? No. Okay? Why are we not seeing ionic forces? Identifying a metal is relatively easy. You don't see ionic forces typically show up because the ability to identify an ionic compound is so quick and easy, they want you to do a further nuance. So if we don't do ionic, what's the next strongest force? How do I know I have hydrogen bonding? So now I could go through, do I have a hydrogen bonded to fluorine, oxygen, or nitrogen? Yes? And multiple answers? No, just one. Okay? That was a lot of work processing. Should you be able to do that quickly in your head? Yes. For the record, that answer was spat out really, really fast by one of your classmates. Theoretically, all of that processing was done in their head. Okay? You have to decide how detailed you need to get. So people, oh, you show all this work. I show all this work not for the top of the class, but for the bottom of the class that needs to recognize the steps to get through. Okay? Make sense? We good? Your turn. What questions do you have? Or I just start flipping random pages.
Could you do something in chapter 12? Once you do that?
Chapter 12 in the study guide, you're saying? Or chapter...
Oh, not the study guide. Chapter 12 in like with homework and that kind of stuff, that kind of situation.
as in straight from the homework, or do you want me to pull something from the book?
Dealer's choice.
Okay, the book's easier. Unless someone has a specific homework question. Joe, you're looking at something awfully intently. Do you got a question?
No.
Okay, just checking. Let's pause the recording. This is dumb. Okay, so let's just look at this first one. We're being asked for the product. Remember that whole balancing thing? That balancing thing can come in handy because that can help you potentially say what happened in it. Okay, to a certain extent. Okay, a certain extent because, oh my God, that's a ton of reagents in the middle there, and that's going to be really hard to separate and segregate and all that information. Okay, first approach. Okay, did you spend the time to memorize the reagents? Let's say yes. Okay, if you spent the time to memorize those reagents, that particular sequence of reagents is an addition reaction, okay, which we've got to tip off because we start with an alkene. And that addition reaction takes a pi bond and it turns it into H and OH. Okay, so I could now go through, draw out my structure, and I want to add H and OH. But dang, could it have been added this way? Yeah, well, both of those, if all I've memorized is H and OH, okay, so what I now might try and do is go through and look at the answer choices and see, do I get both of those answer choices?
Yeah, you just wrote the same thing twice.
Good thing I wasn't recording yet. I was. Okay. Are both of those answer choices?
They kind of both are, yeah.
Oh, it helps if I draw the structures right. Sorry. My bad. Which becomes the other part. If you're drawing things out, you do have to make sure you're following that flow correctly. Okay? So that they both are. Say, oh, well, now I can't answer anything. You just took the question, okay, on new content that you haven't spent any time really studying, and you went from a 25% success rate to a 50% success rate. That's a good thing. Okay? Very minimal effort. Did you memorize the reagent, what it's tied to, what it does? Okay? You can try to go through and memorize more pieces to it. The more pieces you add to memorizing this one thing typically means the more pieces you don't have memorized of something else. So you have to walk that line carefully and decide what's best for you. Or you're just a supercomputer brain and you can memorize everything. That's fine too. Okay? So what would be the useful extra piece of information that we should memorize to this?
Maybe it goes to the more substituted or less substituted.
I appreciate that. That was a good way to phrase that. That made me feel a little happier. Okay? Okay? where do our substituents go with this particular reagent? Okay? Which piece should we focus on, the H or the OH? That's a harder question. Or a coin toss, right? Doesn't matter. So that's the wording I didn't want to hear, but that's okay. Okay. Everyone goes, oh, the H. Okay, and that I kind of get it, and you're trying to memorize Markovnikov, which is great, but there's a problem with memorizing the H. Look at your answer choices. There's no H shown. So if you've memorized this H, you now also have to realize that you have to include that H now in each of those answer choices so that you can now make that assessment. So I would argue if you're going to memorize, don't focus on the H, focus on the OH, because we can't imply the OH. Okay? Is that going to cause a shift away from Markovnikov? Yes, thankfully. Okay? But that's up to you to decide how to do that shift. Okay? And if we fall back on Markovnikov, it talks about the H going to the less substituted spot, which means the OH goes to the okay? Which then means that's wrong, that's right. I have my answer. With just a little bit more information. And a little bit more information that's directly relevant. Markovnikov isn't necessarily going to be directly relevant because we aren't seeing the H within our answer choices.
Unless you understand implied hydrogens.
Unless you understand implied hydrogens. Remember, if we're starting to memorize things, what are you starting to forget? You have to be able to hold all of these things up at once. One of those things is going to fall, and the more you try to cram in there, the more likely things fall. So what I'm trying to establish is patterns that would allow you to navigate that as best as possible. Okay? For this particular reagent, absolutely, hands down, 100%, this is what I would do. Okay? The chemistry behind it is not pleasant, okay, because it adds weird purple streaks. There it goes. Okay. The chemistry behind it is that we have to remember that mercury has access to electrons. Okay? So that what happens when we run this particular reaction is that mercury coordinates to the pi bond, and I dropped that carbon again. Jiminy Christmas. Forming our mercuronium ion, the OH from water, not actually hydroxide, comes in and does a backside attack, okay, ejecting the mercury, and because the mercury is such a great leaving group, it doesn't want to be positive, it attacks that most substituted position, because that's the most stable kind of carbocation it forms. That's what gives me the placement of the OH. Do I want to memorize all that extra information? I don't know. That's your choice. Me, yeah. I've been doing it longer, though, so that's not really a fair question. Make sense? Okay. I'm going to leave that stuff up there that we memorized. Okay? Why would I leave it up there? What are we going to move? Well, first, were there questions about that one? Good. Officially, what did we say the answer was? C. Okay. And we can now move to the next question. What do we see in the next question?
Something relatively similar.
Something really, really similar. I see that same mercury substance popping up again. And I go, oh, okay, what does the mercury substance do? It does the same thing. It adds H and OH across the pi bond. So I look at my starting material. I don't know why I had to draw it again, but I did. And then I'm just slowly getting sloppier and sloppier with how I draw it. Again, recognizing I could have had those two options, but I've memorized that extra more substituted, which then means my answer choice is that, right? Because there it is, shows up as answer choice B, and I go, hooray, and I move on.
Should it be the other one?
Should it be the other one? Nope.
Just making sure.
No enals. Why is that answer wrong? What's that?
What about that PR?
Man, I'm having a hard time with my zoom on this. Okay. When we look at that reagent, that's H2O. Okay. When we're doing this addition, it is adding H and O. It's not technically adding OH. It's adding O. That H is just along for the ride. That means that can be anything. It's not H, it's R. It could be anything connected to that oxygen that doesn't affect its chemistry. Okay? We can answer that question in a second. Okay? Why is that important to us? We can now move down to that next piece, and we see PROH. If we look at our addition, let's color code this a little bit. Okay, our addition adds the oxygen and an R group. There was an extra H on there that was lost through the course of the reaction. That's how we did that reaction, right? Okay. So if I now go through and take this reagent and fit that into the pattern, what do I have? I've got the O, I have the H, and I have the PR. And this is where there's a giant question. What is PR? Do I care?
Probably not.
Why not? If I've memorized my proper system, it's not adding OH, it's adding OR. What is the R? Is that answer choice there? Do I need to know what PR is? No. Why not? It did absolutely nothing. Except those people that memorized mercury doing H and OH. They got shafted. Because what they spent time doing was just memorizing the outcome in a niche scenario and missed the secondary scenario. What's the change that I'll see people do? They'll go through and say mercury with water is the addition of H and OH, and mercury with an alcohol is H and OR. It's the same flippin' chemistry. Why did you memorize two things when you could have got away with one? Okay? And I can tell you the answer is because you're looking at it each independent new pieces of information. They're not new pieces of information. That's why we track the chemistry behind what's happening. Kind of, sort of?
So, I'm a little bit confused. Why would we keep the PR but not the H?
So why would we keep the PR and not the H? That has more to do with the identity of what that PR is, which is where we're going to go to next. Okay, conveniently I erased that whole mechanism thing. Can I do it without losing? Oh, it's a new structure, so. We've got our mercury, right? With the positive charge, OAC, really good leaving group. Okay. What happens? I'm going to put an H there, PR there. As our electrons come in, kick that out. What do we get? Try again. I get a positive charge on that oxygen. Does oxygen want to be positively charged? No. So what does it try to do?
Eject something. Pull the electrons from one.
I like that phrasing better. Eject isn't as bad as leave something or something leaves, but I just couldn't process eject. So it has to take the electrons from somewhere. Okay? Where would it preference taking the electrons from?
So
It goes back to our electronegativity trends. If I've got some trends in electronegativity, oxygen is going to remove electrons from the least electronegative element connected to it. So we could look at carbon versus hydrogen. Hydrogen's lower in electronegativity. Okay? So hydrogen's preferenced over that carbon. Well, what the hell is PR? Have we memorized anything about naming? 1 carbon. Methyl. 2 carbons. Ethyl. 3 carbons. Propyl. How would you abbreviate propyl? PR. 1, 2, 3 carbons.
Would it be a lot easier to just write that out and more clarified?
So there you run into the weird gray area and you're barking up the wrong fight or preaching the choir or however you want to look at it. Okay? Yeah, I think they should draw out the structure. Okay? Why are they also going to show it? Okay? Well, if you're a chemist, are you going to encounter PR as an abbreviation? Yes. Okay? So what the test is written for is not just people who aren't going to become chemists that need to understand the chemistry, but there's also a significant portion of people that are going to become chemists, and it's written for those people.
But then how do we know it's not that?
How do you know it's not that PR? Tell me where to point.
Bottom by cesium.
By cesium.
Is cesium? Oh, no, not cesium. CE. I'm sorry.
Sorry, okay.
When I see CE, I think
PR,
cesium.
okay. I knew it was somewhere down there. I couldn't remember where it is. Why is it not promethium?
So you know the
Why
name.
do we encounter in organic chemistry?
You mean, what about on the very first lecture, we said we simplify the periodic table and we remove 95% of it and we only look at these elements? Is PR one of those?
Was
No.
Mercury one of
Why
those?
not? Mercury was not one of them either, which is a
Okay,
fair
well,
play.
There stands my point.
Sure.
So if Mercury wasn't one of them, why
Sure.
can't Promethean be one of them?
You're right. You're right. Okay. So let's push to it even further. Do you know anything about electronegativity of promethium? No. You know nothing about it. You know something about carbon and hydrogen. So you can go out on a limb and say, I have no idea. I'm going to make up something about it. Or we could try and fit something within the context of the class. Okay? Which is fine. Take your choice. Okay. Next one. I'll take that as a yes. Note for these first 2 questions, what was being addressed?
Addition? Rear.
Right, but what part of the addition? Did we care about the mechanism?
Sort of. I mean, I guess not really. No.
We didn't really ask any questions about the mechanism. We could have just memorized the addition is pi becomes H and OR. And the OR goes to more substituted. The conclusion of that is based off of the mechanism, but I never asked anything about the mechanism. Okay? So one common complaint that students might throw out is that, well, why do I need to know mechanisms if I could just memorize the answers? You're right. Okay? If you could just memorize the answers, you'd be good. You can't memorize the answers straight off the bat. I'll just say you're wrong. Okay? But then what happens when we move to the next question? What is the question asking about? The intermediates. And where do intermediates come from? The mechanism. Okay? So again, you can choose to not deal with the mechanism or the chemistry. That's okay. I get it. Don't like it, but I get it. But you will encounter questions like this that are now very specifically asking about intermediates. Those intermediates come about from understanding the mechanism. And if you understood the mechanism, what happens with the previous 2 questions? You also got their answers. So understanding the mechanism allows you a broader sense to be able to do everything. Understanding takes time. There's a balance you've got to play. So figure out your balance. Okay? And when I say that, I mean you have to figure, I can't tell you that. That comes to your decisions. Right? We've actually already drawn out the intermediate for this reaction. Which one is it? That was the mercuronium ion coordinating to the pi bond. Okay. Why are they throwing the B in there? Okay, because you're like, oh, I see the BH4 there. More than likely they're throwing the B in there for a different reason. What other reagents take a pi bond and turn it into H and OR? Or technically that one's actually going to turn it into H and OH. BH3 THF, followed by sodium hydroxide and hydrogen peroxide. If you've moved into this channel of memorization, you're going to start to conflate the different reagents. That's why that reagent is there. It's not because of the BH4, because theoretically you should be able to look at the BH4 and say that's negatively charged. That's not going to react with the alkene. But if you've memorized BH3 does H and OH, you might see the boron and immediately say that that's your intermediate. Okay? So what they're trying to check or challenge is, did you memorize things? If you did, well. Okay, you get that one wrong. If we look at the other reagents, structure 3 is a follow-on mechanistic product from the BH3, and structure 4, what's going on within structure 4? Okay, because what happens to the enantiomer? What happens to structure 1? What's the next step? Does it produce the product right away? No. It forms another intermediate, which means, is there a possibility to select multiple intermediates? Yes. Okay, so we like answer 1, so 1 only looks really great, but I also have 1 and 4. So I have to evaluate what's going on with 4. What happened in 4? Water did a backside attack. Isn't that what water does to the mercuronium ion? Yeah. So is it 1 and 4? No. Why? Where does the oxygen do the backside attack? The more substituted position. And if we look where that oxygen is located at a secondary carbon. If it had attacked the other spot, it would have been tertiary. That is an intermediate for the wrong mechanistic step. Very subtle change in the overall structure. Okay? Great kind of flow, unfortunately did the wrong attack, and that's why that structure is wrong. And so your answer is now only 1. Make sense? Okay. Note how subtle the change can be. Okay, so you've got to be real careful and kind of methodical behind that approach.
Now I've got a stupid question for you. Why not 3?
What's the deal with 3? 3 has all sorts of issues going on with it, actually. Okay? Where is 3 coming from?
Oh, yeah.
3 is coming from the reaction with BH3. Okay? Even then, it's convoluting mechanistic steps because the boron, when it adds hydrogen to the other position, not oxygen. The oxygen replaces the boron. So I don't have oxygen and boron on the same structure at any given time. Okay? So 3 is a mishmash of all 3 mechanisms. Technically 2 is also. Okay? Again, very mechanistic. Have you spent the time to really understand it? If not, let it go. Okay? Which brings up another point towards processing the exam. Okay, we've already addressed, number 1, the exam is not 70 questions for anybody in this classroom, right? Remember that conversation? Okay, some people, yes. There are 70 questions, okay, but your target isn't 70 questions. Okay, so you could absolutely let some questions go. Right? In the process of letting those questions go, you can spend more time per question. Is this a question that you're likely to get right? Again, that's a personal statement. You're like, oh, yes, because I've seen it. You won't have seen the questions. So saying yes because I've seen the question isn't helpful because that's not true. Okay, so you might say, yes, I'll get it right because I've seen that question before, which means when you get it, you get the answer, you spend the time. If you look at it and you're like, I didn't do anything with mechanisms, don't spend any time on it. Okay? As soon as you see it and go, stop answering it or bubble in an answer and move on. Okay? Because if you continue to panic mode look at it, all you're doing is eating time out of those questions that you could be getting right. Okay? Time management is an important life skill. Kind of makes sense? I have also had this conversation with a couple people. When we look at our exams, okay, everybody's complained about the length of the exam. The length of the exam matches the final exam. Okay? It's about 1.5 minutes per question. That's all you get. Okay? For your normal exams, you didn't have a target to aim for. You were just hoping to get everything right. Okay? Which shouldn't be hindsight, but you should recognize that was never a reality. Okay? And what you were trying to get right is the questions you knew. So you should have focused on those to maximize your points. Okay? Then what the test has done is an accurate assessment of what you learned. Okay? The final exam is different because you're now not trying to answer all questions. You're trying to answer only a subset, and you know what that number is. You can use that and leverage that to better success on the exam. So do it. Kind of, sort of? Okay. Should we drop in the last one? Okay. Which will be helpful for going back and reflecting about that mechanism. Okay, I'm going to leave up the addition for that first one. For this one down here, okay, again, did we spend the time to try and memorize some pieces? Hopefully, yes. This is an addition reaction, which means the pi bond converts to H and OH. This is a nice subtle change because this isn't OR, this is OH. Okay? Admittedly, they screwed me, and we'll talk about why they screwed me here in a second with how they formatted the question, but H and OH. Okay? What other thing could we identify here? Just like we did up there with our mercury reagent, we want to identify where the primary group goes. Pointing at the H probably isn't useful because it may or may not be specified. We'll talk about why it might be in this case. So the OH is more relevant. Where does the OH go? The reagent is a different mechanism, and this is a neat one because it takes the OH to the less substituted. If it went to the more substituted, it does the exact same thing as the mercury reagent. Why do we need two reagents to do one thing? Okay, so there's a subtle tweak within that. The OH goes to the less substituted position when we're looking at the boron reagent. Okay, so we could go through this system. Start again with our draw out. We want to add the H and the OH, which means my product should look like this. Okay? We should immediately have issues. What issues do you see? There's no OH. What the hell? Okay. They throw on a bunch of D's. What are the D's?
Does it matter?
Fair question. I don't know why I didn't ask myself that. We asked it for the earlier question. No one put a question mark. That's what I'm going to say. You tell me. What do you think? Does it matter?
Considering that I don't know what the hell D is, probably not.
I was just say I have no idea what D is. D has never come up in my life before. It absolutely should have. Whether or not it did is an entirely separate question.
That's what she said.
Different levels with that one. Where did the OH come from? You might need to know what the D means. Okay? If you don't acknowledge where the OH came from, yeah, you're probably going to need to know some information about what that D is standing for over there. The OH is coming from hydrogen peroxide in the second step, H2O2. This says D2O2.
Oh my god. Deutronium, or whatever it is.
Close enough.
Yeah.
Okay? So whatever that D is has the same bonding patterns that we would expect for hydrogen, because we would typically see this as H2O2.
Oh, so it doesn't matter.
Okay? So what we could say is it doesn't matter. I'm just going to turn the H into a D and not worry about it. Okay, so cool. Let's run with that. We'll come back to what D means in a second. So we'll just say, okay, it's D. Don't know why, but ta-da, there it is. Do we have another issue? If we go through and look at these answers, we've got a ton of stereochemistry spitting out through this. Okay? We might be able to take a whack at some of this. In our overall process, what did we go through and do? We just added OD to the less substituted. What happened in answer choice A?
It's in the less substituted. And the most substituted.
And the most substituted. That's not right. Next one.
It's in the most substituted.
Next one.
It's the correct one. It's in the less substituted.
Less substituted, and the next one?
There's a D.
The, is it interchangeable to put H as D? That's a good question. I really don't know.
We'll come back to that in a second. Okay? So how can we differentiate these two answers? Okay? One of the things is that when we memorize this reagent, there's another caveat we have to associate with this. Okay? That caveat is how the substitution happens. Okay? And again, it can be mechanistically understood, or you memorize the words or know what those words mean. Okay? The words that we're looking for are a syn addition. These two things are added on the same side. Okay? Where did the H come from? The boron reagent. If we look at the boron, what's next to the boron? Is it D? No, it's H, which means when I look at my answer down here, I could also specify that position must be H. Do I know my answer? Yeah, I don't even need to know about this added same side nonsense. Like, that falls off the plate. I don't have stress about it. Okay? But if I had hyper-focused on that D, now I'm really confused about what's going on. Okay? Is there still more information that could come out of this? Yeah. Okay? The H and our OD are added on the same side, which means if I make the H wedged, what must the OD be? Wedged, because they're the same side. And when I go through and look at the only answer left, because we eliminated everything else, the H and the OD are added on the same side. They're both wedged. Could they have been dashed?
Yeah.
Yeah. Why did I say wedged?
Because that's one of the answer choices.
When I looked at the answer choice showed it as a wedge. I'm trying to match as close as possible to what the answer is, so I don't have to think as hard. Okay? If I'd shown dashed, I would have also had to show dash, and that would have been the enantiomer that they're just implying out there. Kind of, sort of? So we're trying to take advantage of small bits of information along the way. Everything that the ACS does looks at all of those pool of information. When we run addition reactions, I've got mercury reagents that add H and OH. I've got boron reagents that add H and OH. So I could ask a question, which reagent do we do? How do we differentiate those? Those are based off of less substituted versus more substituted. Maybe I want to look at the boron reagent and say, do you actually know something about how it happened? Do you understand the syn addition? So now what I'll go through and do is show within my answer choices both syn and anti. If you knew the syn addition, you're done. You got it. If you knew the mechanism, you had to draw it all out, but you also got it.
So in the end, knowing the D didn't matter.
So in this process, we didn't actually need to know the identity of D. Didn't change anything. What is the identity of D?
Deuterium? Something like
It's close enough. Deuterium. Okay. What is hydrogen?
proton.
Hydrogen is made up of a proton. So if I look at trying to identify an atom of hydrogen, it is proton. Ta-da. Okay. What would its mass be? 1. Is its mass 1? No, it's close, but it's not exactly 1. Why is it not exactly 1? It's an average. An average of what? All the different hydrogens. Well, if hydrogen is 1 proton, how do I get different hydrogens? We add a neutron. Okay? So hydrogen that is 1 proton and 1 neutron weighs slightly more. When I average that with the hydrogen that is just a single proton, that's going to change the output on my periodic table, because the periodic table is the average atomic mass. That's why we get all these weird decimal points, among other reasons, but that's the easiest explanation. Okay? Well, I have this new hydrogen, this new thing. If I want to talk about it, it might be nice to have a name associated with it. Okay? So if we get real fancy, physicists love this. Okay? We look at hydrogen that has just 1 proton, and we would call it protium. You have to add the IUM because it sounds cooler. And I have protium, da-da, hydrogen. Okay, what happens when I move to the hydrogen with 1 neutron? Well, its mass changes. It changes to what? 2. Let's be inappropriate. Why not? Dropped a deuce. Playing cards, I threw a 2 down, right? And we call it deuterium, referencing the root name that hydrogen has 2 subatomic particles. What happens if we add a third neutron or second neutron? How many particles do we now have? 3. Tritium. Yeah. Okay. Do we do this with all of our other isotopes? No, why not?
Hydrogen special.
Because hydrogen is sort of special. Why would hydrogen be sort of special? Remember who did this? It's our physicists. And what do our physicists like to do?
You douchebags. Oh, that's it.
Do our atom bombs, and we're looking at hydrogen. There you go. Ta-da. So they studied hydrogen a whole bunch, and since they're studying hydrogen a whole bunch, they want to be very particular about what atom of hydrogen they're looking at. So instead of saying it's hydrogen 2, hydrogen 3, hydrogen 1, they say protium, deuterium, or tritium, because they feel that's easier.
Does that not change the chemistry very much?
Question for a different day. You can ask me after class. Sort of. Sort of. You could make the analogy to people. We're all people. Does the mass of an individual person change how that person interacts with the world?
Yeah.
Okay.
Have you seen my 500-pound life?
No, I haven't.
No, me either.
Okay. Next.
Here's the next page.
You want to keep doing these reactions? No. Okay. Thank you. Yeah. Really, this is all the stuff you just want to memorize. For the record, for all that stuff that you should be going through and memorizing, what should you be doing right now? Writing a list of all the things you want to memorize so that Tuesday or Wednesday of next week, right? Sounds somewhat depressing, but it's not intended to be depressing. You're not going to learn anymore. You're done. Okay? You're full on done at that point. The only thing that you can hope to do is to increase the memorized knowledge. So if you've been creating a list of the things you need to memorize, guess what you can start looking at on Tuesday and Wednesday? Your list of things to memorize. That would be useful. That's why we take notes. It's the same response I do. What does optically inactive mean? Okay, that's probably the best word to throw out. Okay, so we're looking at a symmetric molecule. Okay, symmetry could be a little bit weird. Okay, really what we're looking for is an internal mirror plane. which is also a dangerous thing to say. Okay? When we're looking for internal mirror planes, sometimes it's really inherently obvious, sometimes it's not. Okay? So for instance, if I look at, let's just do that. Okay? How many mirror planes are there?
1,
2.
2.
Okay? Absolutely the one right through the middle, that's easy. Where's the other one? Cutting through the plane of the paper. Yay, mirror planes. Okay? Sometimes they're obvious, sometimes they're not. It can be tricky. Some people are really good at it, some people aren't. I tend to be one of the people that is in the aren't camp. Okay? So, for the record, since I know I'm weak at it, what would I do if I encountered these questions?
Cry.
I'd hold that. Draw them out. No. I would skip it. I'm going to move on. Nope. I'm probably going to get it wrong. Not going to waste my time. I'm going to come back to it when I feel like I have time, if I have time. Okay? And at the end, worst case I haven't gotten to it, I'll just bubble in a random answer. Okay? So, internal mirror planes. Okay? What else makes this question particularly challenging? God, this is an awful question.
Is there also something with chirality if they're equal and R and S is?
Okay, I appreciate that word as well. We can also bring in this concept of chirality. Okay, because you'll see that word. We'll use lots of synonyms for different things. So optical activity can be tied back to chirality, okay, or achirality, depending on what you're looking at. An optically inactive molecule is achiral. Okay, it has the internal mirror plane, all that fun stuff. Okay, so the internal mirror plane is what you're looking for. Symmetric, I don't think you would see in a question, but achiral or optically inactive, those terminologies would show up frequently. Okay, trying to find that internal mirror plane. Why has this question become extra particularly obnoxious?
You have to do multiple.
It's not even just do multiple. That is a layer of complexity behind this. There's 3 different ways to draw those individual molecules. Okay? Which means you have to interpret 3 different structures. You can't just be like, I'm going to convert all the Newman projections across. I have a Newman projection, but not all of them are Newman projections. Okay? I also have a Fisher projection. This is going to require lots of kind of work to think through and reasoning, and each of those cases is requiring the 3-dimensional space relationships that we were supposed to have learned back in Unit 1, okay, that are really hard to master. Okay? So if you understand some simplifications, you can get through this. Okay? For me personally, looking at this, as much as I hate Fisher projections, I would probably start with the Fisher projection, okay, and try and look for an internal mirror plane. Okay? I might go right there, I have an internal mirror plane because the OH reflects to the OH. But then CH2, CH3 does not reflect across. Okay? So with that one, what am I going to say? No, that one's chiral. Right? And again, I did preface enough, right, that I'm horrible at this. Okay, so that one's chiral, which means that one's my wrong answer. So I could go through real quickly. 3's wrong. Damn it. Down to 50-50. Okay, and even there, like that was a relatively minimal time investment. I might just say I went from 25% odds to 50. I'll accept the 50 and move on. Okay, you have to make that decision. So between whittling through the rest, I would probably look at structure 1. Yeah, and what would I do with structure 1?
Maybe convert it to a Newman projection? Newman.
Yeah, to be honest, I'm oscillating back and forth between this. If I was going to convert it to a Newman projection, I wouldn't look at structure 1, I'd look at structure 2.
Well, we already know.
Well, actually, I need to look at structure 1. I have to look at structure 1. Nuggets.
2, we already know is an answer.
Okay, so with that, we do have 2 options. You can convert it into a Newman projection, or you could go line angle. Okay, that front carbon, we'll call my purple dot, call that red. You are allowed to use multiple colors if you want during the exam. That is entirely up to you. You just have to supply your own multiple colors. The OH is going straight up, CH3 is to the right, H is there. The back one, CH3, H, OH. Does that look like an internal mirror plane already?
Yeah, there's an internal mirror, right, so it's there. Like straight across.
That makes me really nervous.
How are you supposed to be sure, though, without the wedges and dashes?
So remember the Newman projection identifies all the wedges. I think what you're saying is from that drawing
Yeah.
that was
one.
provided you. Well, from that drawing, this is technically what you're looking at. Does that make you happier?
No.
Yeah, it doesn't make me any happier either. Okay. What they've done within that drawing is it's oriented in a way that represents that three-dimensional space without having to use wedges and dashes. It's dangerous, but what they're showing is the transition to becoming a Newman projection. Okay, which is why we could draw the Newman projection, or why I could draw the Newman projection so fast. Okay. What they did was took the side view and they started turning the side view out. Okay, by turning the side view out, that's what's giving you this sandworm looking shape. Okay, right? Sandworm. Okay. And these extra dashes in the back are dashes on dashes. Okay, so looking at it, it looks like an utter mess, but that's what they're trying to represent with that. Is that something that you are personally comfortable with?
I just don't like that they didn't put wedges and dashes like stuff, because we always have to put wedges and dashes on stuff.
Did you want to look at that? Because that's what you're saying. If you wanted wedges and dashes, that's what they're trying to draw for you.
Okay.
Okay. Okay. So said a potential different way. If you don't like it, what's your task?
One question left.
Skip it. Move on. Okay. If you go back to the Newman projection chapter, we do walk through that. It's a transitional drawing. You can make the argument that it's allowed to be shown on the ACS. It's not it might actually be a standard drawing. It's just not used except you're going into the Newman projection. So we did not talk about it a lot. At that point, you can say, well, why didn't you talk about it? I didn't talk about it because I thought it was stupid. Okay? And you just have to kind of deal with that, unfortunately. Okay? As we wind down with time, because we are done, you will encounter things that you have not seen before. Okay? That's going to happen. There's a crap ton of content throughout OChem 1. Okay? You have to decide what to do at that point. You use the tools that you've been taught to try to predict what would happen, or you're like, I have no clue, I don't remember anything about this. And at that point, what you're hoping for is that there's some, I'm not trying to say it this way, but it's the only way I've got to say it, some higher power that's looking over it and saying, that question is not an appropriate question to ask. I'm removing it. Okay?
Does that happen sometimes?
Yes.
Would they look at the test after the fact, or is that before the fact?
Who's the higher power in this scenario?
ACS?
It's me.
Oh, you.
Yeah. No, because ACS, and I don't report to ACS for this very reason, because I think there's things that are inappropriate to be asked, and I don't think those should be scored. Okay. What I could go through and do is ship all the scores to ACS. I don't do that. shouldn't have recorded that.